So, in the last few lectures, we have been looking at the separation of variables procedure in different in a finite domain in a Cartesian coordinate system. So, you have a finite domain.
One minute, sir.
Yeah.
The mic is not put properly, sir. Okay, sir, you can start, sir.
In the last few lectures, we were examining the separation of variables procedure for solving for the temperature field, the unsteady temperature field in a finite domain in a Cartesian coordinate system. And if you recall, the scaled temperature and distances were all defined in this manner, and the equation and the boundary condition, when expressed in scaled form, are independent of any parameters. We had expressed the temperature as the sum of a steady plus a transient part. The steady part is a linear function. It varies from 1 at 0 to 0 at 1. The transient part satisfies the same equation as the original temperature. However, the boundary conditions are different. The boundary conditions are homogeneous. T star is equal to 0 on both surfaces because I have subtracted out the steady solution. And then I express the transient part as the product of two functions, one a function of position and the other a function of time, and substitute into the equation, divide by f times z, and both sides of the equation are constants. That constant has to be negative, so that the temperature transient part decreases exponentially as time progresses. For the spatial component, I get sine functions, and the requirement of homogeneous boundary conditions on the bottom and top surfaces implies that this coefficient has to have discrete values I times pi, where I has to be an integer. And therefore, the temperature can be expressed in this form, and the coefficients are determined from the initial conditions, because this form of the temperature field that is shown here, okay, this form of the temperature field satisfies the equation. It satisfies both boundary conditions, because the transient part is 0 on both boundaries. Initial condition is that the transient part has to be negative of the steady part at t is equal to 0, and therefore, this is the initial condition. It effectively contains an infinite number of coefficients a I on the left. However, each coefficient can be uniquely determined using the orthogonality relation, okay, for this problem. Okay. Each coefficient can be uniquely determined using the orthogonality relation for this problem. And I had shown you how to calculate the coefficients by multiplying both sides by sine of j pi z and integrating from z is equal to 0 to z is equal to 1. The left side is non-zero only for I is equal to j, and it is 0 otherwise. And therefore, this coefficients can all be determined, and we got this solution for the temperature field. Okay. And I had looked at various analytical approximations for that solution as a function of time. At later times, it is sufficient to include just a small number of terms in the series. As you go to earlier times, you have to include a larger number of terms, otherwise you will get spurious oscillations. The temperature might go to less than 0, which is unphysical in this case, because that would imply that the conduction is in the opposite direction at one surface. So, you will get these spurious oscillations if the number of terms included is too small, but at very early times you can also use the error function solution, okay, to get a solution of the equation. Okay. So, I will look at one more example of solution by separation of variables. Okay. And this is as follows. Okay. I have two blocks. bound by two insulating surfaces. Two blocks bound by two insulating surfaces. Let us say of infinite extent in the direction perpendicular to z. I will use z direction starting from the interface between the two blocks, and both of these have height h, and they are made of identical materials. So, they have the same thermal conductivity for simplicity. You could solve it even when the thermal conductivity is different, but in this case we will consider the thermal conductivities to be the same. Okay. And at so, there are two insulating surfaces. So, the boundary conditions are 0 flux, okay. That is partial T by partial Z is equal to 0 at Z is equal to minus H and Z is equal to plus H. At these two surfaces, the derivative of the temperature with respect to Z is equal to 0. And at the interface, of course, the temperature has to be equal and the temperature gradient also has to be equal. Okay. The flux has to be equal at the interface. Okay. And since this material has equal thermal conductivity, okay, both the materials have equal thermal conductivity, that means that the temperature just has to be a continuous function there. Okay. At the interface, the temperature just has to be a continuous function. And the initial condition is that T is equal to T1 at T star T is equal to 0, T is equal to T2 at T is equal to 0. Okay. The physical situation is that I have two blocks of the same material of equal height at two different temperatures. At time T is equal to 0, I bring both of those together, okay, and I want to find out what is the evolution of the temperature as a function of time. Okay. So, that is the physical problem. So, if I replot the blocks here, of equal height, I will define z star is equal to z by h. Okay. So, this will be z star equals 0, bottom surface is z star is equal to minus 1, top surface is z star equals 1. Okay. And in between z star has to be equal to 0. Okay. How will the temperature look? Okay. How will the temperature look? So, if I plot the temperature field, okay. Note that since both surfaces are insulated, there is no heat that is coming in or going out. So, the total amount of thermal energy has to be equal to the total amount of thermal energy that was there initially. Okay. If the materials are of the same, if the two materials, if the two slabs are made of the same material, the specific heat and the thermal conductivity are the same. Okay. So, initially the temperature is going to be T is equal to T1 here, sorry T2 here, and T is equal to T1 on top. Okay. So, the temperature is going to be T1 on top, T2 below. Okay. In the final configuration, so let me just separate this. Okay. They are going to have different temperatures initially. In the final configuration, the two temperatures in the two slabs, the steady state temperatures are both going to be equal, because in the final steady state the temperature has to be a constant throughout. Okay. As long as the temperature is not a constant, there is going to be a flux. Okay. So, in the final steady state the temperature has to be a constant throughout. What that means is that since the blocks are identical, in the final steady state the temperature T is equal to T1 plus T2 by 2, okay, because rho Cp times T has to be the total thermal energy. Okay. So, the initial thermal energy, that is rho Cp into T1 times the height h for the first slab, plus rho Cp into T2 into h for the second slab. has to be equal to the final temperature times rho Cp into 2h. Okay. So the energy balance condition basically is that initially rho Cp T1 into h, energy per unit area, okay, plus rho Cp T2 into h has got to be equal to the final energy when the temperatures are the same in both cases, okay, rho Cp into h into 2h into the final steady temperature. Okay, so that is the condition for total energy balance. Therefore, the final temperature has to be T1 plus T2 by 2. Okay. How would the temperature field evolve at intermediate times? Okay. How would the temperature field evolve at intermediate times? Note that as the temperature field evolves, the flux has to be equal to 0 at the bottom and the top surfaces. Okay, the flux has to be 0 at the bottom and the top surfaces. Therefore, the gradient of the temperature partial T by partial Z has to be 0 at the top and bottom surfaces. The slope has to be 0. Okay. So, since the slope has to be 0, this will evolve in some symmetric manner, okay, such that the slope is 0 at the bottom and the top surfaces. Such that the slope is 0, it will evolve symmetrically in such a way that the slope is equal to 0 at the top and bottom surfaces. Okay. So, that is the physical picture here. Okay. Okay. So, now we have to define the scale temperatures. Okay. I said that Z star is equal to Z by h. That means that the domain goes from -1 less than or equal to Z star less than or equal to 1. Okay. What is the temperature? Okay, T star. Okay. I told you that we have to subtract out the steady temperature, okay, in order to get the transient part. In this particular case, the steady temperature is just a constant. Okay. In this particular case, the steady temperature is just a constant. Okay. So, I can subtract out that constant value. Okay. And divide throughout by that constant value, okay, and divide throughout by the difference, okay, and divide throughout by the difference half of T1 minus T2. Okay. And the boundary conditions are that the heat flux partial T by partial Z is equal to 0 at Z is equal to 0, which implies that I am sorry, at the top surface, which implies that partial T star by partial Z star is equal to 0 at Z star is equal to 1. Okay, that is the top surface. The bottom surface similarly, okay, partial T by partial Z is equal to 0 at Z is equal to minus h, which implies that partial T star by partial Z star is equal to 0 at Z star is equal to minus 1. Okay. So, those are the boundary conditions that have to be satisfied. 0 flux conditions at the top surface, Z star is equal to 1, and 0 flux condition at the bottom surface, Z star is equal to minus 1. What is the initial condition? Okay. At T star is equal to 0, right, initial condition, okay, T is equal to T1 for, okay, the top slab, okay, Z greater than 0, okay, T is equal to T1 for Z greater than 0, okay, and that would imply, okay, if I substitute T1 here, T is equal to T1, I get T1 minus half of T1 minus T2 by half of T1 minus T2. Okay. Just substitute T is equal to T1 in this expression, okay, and I will get that T star is equal to 1 for Z star greater than 0, and t is equal to T2 for z less than 0. Okay. This implies that T star, okay, if I substitute T2 here, I will get minus half T1 plus half T2 divided by half of T1 minus T2. That means that T star is equal to minus 1 for z star less than 0. Okay. That is the initial condition here. Okay. Initial condition is that over here T star is equal to minus 1, over here T star is equal to plus 1. Okay. That is the initial condition, and the boundary conditions are the zero flux conditions. Okay. Okay. Note that in the final state T star is equal to 0 everywhere. Okay. Okay. In the limit, okay, the final state, okay, at steady state, okay, so for T star going to infinity, we said that T has to be equal to half of T1 plus T2. Okay. This implies that T star steady is equal to 0. Okay. I said we had to subtract out the steady part to get the transient part. In this particular case, the scaled steady temperature is equal to 0. Okay. So, the total temperature is equal to the transient temperature in this particular case. Okay. So, you can just solve for the total temperature here because it is just equal to the transient temperature. Conservation equations, okay, it is going to be the same because the equation is the same, the scaling is the same, okay, and therefore, the non-dimensional equation will also be the same. Okay. The boundary conditions, partial t by partial z is equal to 0 at the top and bottom surfaces, both plus and minus 1. Okay. Initial condition, okay, T star is equal to 1 for uh, 0 less than z less than 1 is equal to minus 1 for minus 1 less than z less than 0. Okay. So, it is equal to plus 1 on the top material, it is equal to minus 1 on the bottom material. Okay. So, those are the boundary conditions and the initial conditions. Separation of variables procedure. T star is equal to f of t star z of z star. Okay. Equation becomes 1 over f of t star df by dt is equal to 1 over z d square z by dz star square. Since the transient part has to go to 0, in this case the transient part is the total solution. Since the transient part has to go to 0 as z goes to as t goes to infinity, this has to be equal to minus beta square. And beta has to be chosen so that the boundary conditions are satisfied. Okay. So, that means that z is equal to a sine of beta z plus b cos of beta z. Okay. Note that from the symmetry, okay, from the symmetry this t star has to be equal to 0 at z is equal to 0. Okay. Just from symmetry t star has to be 0 at z is equal to 0, which implies that b is equal to 0 as before. Okay. From symmetry t star has to be 0 at z is equal to 0, that means that b is equal to 0 as before. The condition on beta is derived from the requirement that dz by dz star is equal to 0 at z star is equal to plus or minus 1. Okay. This implies that a beta cos of beta z star is equal to 0 at z star is equal to plus or minus 1. Okay. So, if I plot the sine and cos functions, this is let us say as a function of beta, I plot what is sine of beta and cos of beta. Okay. So, let me use different colors there. Okay. So, the sine function has this shape. And the cos function looks something like this. Okay. What I require is that the slope of the sine function has to be 0, or the cos function has to be 0. Okay. This happens at these locations. Okay. The cos function or the slope of the sine function is 0 at pi by 2, 3 pi by 2, 5 pi by 2, etc. 7 pi by 2, 9 pi by 2, so on. Okay. Or alternatively, when beta is equal to 2I plus 1 by 2 into pi. When beta is equal to 2I plus 1 by 2 plus pi for all values of I starting from 0. I is equal to 0 is pi by 2, I is equal to 1 is 3 pi by 2, I is equal to 2 is 5 pi by 2, and so on. Okay. So, for these values of beta, the solution is equal to the slope is 0 at both beta is equal to at both z is equal to 1 and z is equal to minus 1. Okay. Because cos of minus 1 is the same minus beta is the same as cos of beta. Okay. It is an even function. Therefore, the specific values of beta that satisfy this criterion are beta is equal to 2I plus 1 pi by 2 for integer I. Okay. Beta is equal to 2I plus 1 pi by 2 for integer I. Okay. So, those are the values for which it satisfies this condition. Okay. Therefore, this gives us the solution z is equal to sine of 2I plus 1 pi z by 2 times some coefficient. F is equal to e power minus beta square t. Therefore, the total solution for the temperature So, therefore, the total solution for the temperature T star. Note that this is the same as transient because the steady part is 0, the way that we have scaled it, the steady temperature is equal to 0. This becomes A times sine of 2I plus 1 pi z by 2 e power minus beta square. Beta is 2I plus 1 pi by 2 the whole square, beta square times t. This solution satisfies the equation for any value of I. Okay. This solution satisfies the equation for any value of beta or for any value of I, because it was from this equation that I derived this relation here. This also satisfies the boundary conditions at z is equal to +1 and z is equal to -1 for any value of I, provided I is an integer. Therefore, this total solution is the summation of these functions for all values of I. Okay. Okay. That is the total solution. Okay. That is the most general solution. Okay. Note that in this case I has to go from 0 to infinity, because the solution for I is equal to 0 is not 0. Okay. In the previous case the solution was 0 for I is equal to 0. Therefore, we had just taken it from 1 to infinity. In this case the solution for I is equal to 0 is non-zero. So, you have to take it from I is equal to 0 to infinity. How do we determine the coefficients AI? The boundary conditions are satisfied, and therefore, we need to get the coefficients AI from the initial conditions. Okay. Initial condition at t star is equal to 0, t star is equal to 1 for 0 less than z star less than 1 is equal to -1 for -1 less than z star less than 0. Okay. Is equal to +1 in the top slab and is equal to -1 in the bottom slab. Okay. So, it is a discontinuous function at the interface. Okay. It is a discontinuous function at the interface, and therefore, this solution has to be a discontinuous function at the interface. Okay. So, therefore, at t is equal to 0 the exponential term just becomes 1, okay, and I will get summation I is equal to 0 to infinity AI sin 2I plus 1 by z, okay, is equal to 1 for and is equal to -1 for -1 less than z star less than 0. Okay. We will see how to solve this using orthogonality relations in the next lecture. The only thing I would like to point out here is that we are using a summation, a series of continuous function to actually mimic or to actually reduce to a discontinuous function at initial time. Okay. We are using a series of continuous function such that it reduces to a discontinuous function at initial time. This may seem a little unusual, but it is consistent. Okay. You can actually get a discontinuous function by taking an infinite series of continuous functions. Okay. Of course, at initial time, if it is discontinuous, you would need an infinite number of terms in the series, but still it is possible to represent a discontinuous function by a series of continuous function, provided that series is what is called complete and orthogonal. Okay. I will use the orthogonality relations in the next lecture in order to find out these coefficients AI. Okay. But the procedure, as you can see, is very similar to what we had earlier. Okay. Express it in terms of a steady plus a transient part. In this particular case, the steady solution was 0. So, the temperature was equal to the transient part. Express it as a function of time times a function of z. Substitute in the equation, divide by f times z. Both sides have to be equal to constants, because the left is only a function of time and the right is only a function of z. So, both have to be constants. Constant has to be negative so that it decreases exponentially, and the value of the constant is determined from the homogeneous boundary conditions. In this case, the homogeneous boundary conditions are 0 flux conditions or 0 derivative conditions. in contrast to the previous case where the temperature was 0. And because we have a discrete set of values for beta, we can solve for these, and I will complete the solution in the next lecture using orthogonality conditions. I will see you then.